Alright, so remember I was telling you that there's two kinds of vector multiplication. Today we're going to learn the first one. It's called the dot product. And for those of you in physics, this is work. This is how you compute work. Okay, so this is the definition of the dot product. If you have vector A dot vector B, that's equal to the length of the first vector times the length of the second vector times the cosine of the angle formed by the two vectors. So whenever you have two vectors, you can always, remember you can move them around, right? You can always move vectors around as long as they have the same length and the same direction. So you can always put two vectors tail to tail like this. And so when you put them tail to tail, they form an angle. Okay? So to compute the dot product, it's going to be the length of this vector. Let's say the length of this vector is 3. The length of this vector is 4. And say that this angle is 60 degrees. What would be the dot product of these two vectors? Well, according to the definition, it's the length of the first one times the length of the second one times the cosine of that angle, which we know is 1/2, and you get 6. It's a number. It's a scalar. That's why work is a scalar quantity. So, in some books, most books call it the dot product, but some books actually call this the scalar product. That's because if you multiply two vectors in this way, you get a scalar as your answer. Okay, but see, the problem with this again is you gotta draw the picture, you gotta measure each vector, you gotta compute that angle. So that's why it's better in component form. Now, tonight's homework, you have both 2 and 3-dimensional vectors, so I'm just going to show you the 3-dimensional one. And then, of course, you can extend it to 4 dimensions if you want. So let's say two vectors are in component forms. Let's say vector A in component form is A1, A2, A3. So this is a 3-dimensional vector, right? X component, Y component, Z component. And vector B is also in component form, B1, B2, B3. To compute the dot product, all you have to do is you multiply the two X components, you multiply the two Y components, and you multiply the two Z components, and then you add them up. And see how you're going to get a number? Yeah, so the dot product is simply a number, but we can do a lot of good things with the number, just like a determinant. It's a number, but you can do plenty of things with it. So what do we use the dot product for? Well, mostly to compute angles. So anytime you see a problem, and tonight there's going to be plenty of problems. In fact, there's going to be several on the quiz on Thursday. It's going to say, find the measurement of this angle. Anytime it says, find the measurement of the angle, this is what you're going to do. You're going to use the dot product. It's that simple. Okay, so what we're going to do is, here's the definition of the dot product. We're just going to solve for cosine theta. Okay, so how do I get rid of these two? Would you just divide it on this side? Okay, so cosine theta is equal to the dot product of the two vectors divided by the length of A and the length of B. So this is what, anytime you have to find any angle measurement, whether it's 2, 3, 4, or 10 dimensions, that's the formula you're going to use. Okay, now let me show you how to use it. So let's take a look at a 3-dimensional, so we're in 3 dimensions, but I'm just going to draw it in 2 dimensions. So let's say you have A, B, C. Give me some coordinates for A. How creative. 3, 2, 1 then. Okay, what are the coordinates of B? Let me think. 6, 2, 3. And the coordinates of C are 2, 1, 2. I know I'm writing something different because I want to make the problem come out nice. Okay, so in space, you got these 3 points and they form a triangle, right? Compute this angle. Now, of course, if you want to, you can use the distance formula to compute this, this, and this, and then you can use the law of cosines to figure out this angle, right, if you know all three sides. And that will work, but it's a little messy. That's why it's easier to use vectors. So, what two vectors form angle A? AB and AC, right? Okay, can we componentize each one? Yeah, we learned how to componentize. This is like last night's homework, huh? So how do you componentize a vector if you know the 2 points? Hey, you better be able to do this on Thursday. Head minus tail. If you don't go head minus tail, your vector's pointing the wrong way and you're going to be fired. So 9 minus 3, 0 minus 2, negative 2 minus 1. That's how you componentize vectors, head minus tail. Okay, what about vector AC? Componentize it. Head minus tail, head minus tail, head minus tail. Okay, now once you got the vectors in component form, just do this thing right here. It's so simple. So let's call this angle theta, that's what we're trying to find. So the cosine of this angle is equal to the dot product. Now, how do you compute the dot product of two vectors? Well, I just erased it over here. It's simple. You multiply the x components. Okay, you know what? I'm just going to put it here. Multiply the x components, multiply the y components, multiply the z components, and add them up. That's how you compute the dot product. It's that simple. And then you have to divide it by the length of this vector and the length of that vector. Okay, how do you find the length of this vector? This was last night's homework. Hope you guys are good at it. What's the length of this vector? How do you find the length of a three-dimensional vector? The square root of this squared plus this squared plus this squared. Because in 2 dimensions, don't you just go the square root of this squared plus this squared? So in 3 dimensions, you go square root of this squared plus this squared plus this squared. And in 4 dimensions, you just go, like if you have a 4-dimensional vector, how about 2, 3, 5, 7? Then you just go square root of this squared plus this squared plus this squared plus this squared. Okay, so let's see if we can do this in our head. That's why I picked nice numbers here. What is the length of this vector? Square root of this squared plus this squared plus this squared. 3. See, that's why I have to think to make it nice. What about this vector? What's the length of this vector? The square root of this squared plus this squared plus this squared. 7. I could just make up any numbers and make it come out ugly, radical 85 or something, but I try to make it nice. Okay, now compute this. So cosine theta is equal to negative 12 minus 2 minus 6. What is that?
Negative 20.
Negative 20 over 21. So therefore, what is theta? That's not a number we know, so what do we do? Cosine inverse negative 20 over 21. What does that negative sign tell you? This angle is bigger than 90 degrees, right? Because what is the range of cosine inverse? From 0 to pi, right? So that's why if that was positive, the angle would be acute, but if this is negative, it's going to be bigger than 90 but less than 180. It's an obtuse angle. Anyway, so anytime it says find an angle, that's what you do. It's very simple. Componentize the two vectors that make the angle, and then use the dot product thingy. It's very simple. But then you gotta practice it, that's the thing. Okay, now, how do you tell if two vectors are parallel? Now, every year, this is what students say. Oh, they have the same slope. But the problem with slope is it's a 2-dimensional concept. There's only slope in 2 dimensions, rise over run. Once you get to 3 and higher dimensions, there's no such thing as slope. So, how do you tell if two vectors are parallel? Okay, you know what, I'll just tell you. One is a multiple of the other. So for example, if this vector is 2, 1, 3, and this vector is 6, 3, 9, how do I know they're parallel? Because this is a multiple of that, right? You just multiply each component by 3. If one vector is a multiple of another vector, then they're parallel, because they're pointing in the same direction. How do you tell if two vectors are perpendicular? And of course, every year they say, oh, the slopes are negative reciprocal, but again, once you get out of 2 dimensions, there's no such thing as slope. So what do? Well, if 2 vectors are perpendicular, then wouldn't this angle be 90 degrees? Right? That's what perpendicular means, right? It makes a 90-degree angle. What is the cosine of 90 degrees? 0. And if a fraction is equal to 0, doesn't that mean the top is 0? So how do you tell if 2 vectors are perpendicular? The dot product gotta be 0. Okay, let me give you an example. How about 2, 1, 3, and 5, 2, negative 4. Are these 2 vectors parallel? No, because one is not a multiple of the other. Are they perpendicular? Well, we need to test it. How do you test it? The dot product gotta be 0. How do you compute the dot product? Multiply the x components. Multiply the y components. Multiply the z components and add them up. 0. Therefore, they are perpendicular. So if you were to draw these 2 vectors in space, they would make a 90-degree angle if you put them tail to tail. Okay, I mean that's pretty much the lesson, but there's a lot of things like there's several problems where it says to, like, for example, problems 4 and 5. Guarantee one of those is going to be on the quiz. Okay? Like, you know what? Let me start you off on number 4, because although I did all the problems, right, on the video and on the written solutions. So, okay, here, I'm going to start you on number 4. Given the points A, 4, 0, so here's A, 4, comma, 0. What time is it? We got 4 minutes. And B, negative 4, 0. Anyway, problem 4 and 5 are pretty much the same problem. Describe the set of points P, so here's a representative point P, such that the length of vector AP plus the length of vector BP is equal to 10. So basically, you just do what it says to do. Okay, where is vector AP? Where is vector BP? Can I componentize these 2 vectors? Yeah, you go head minus tail. What is vector AP? Head minus tail. Come on. If we can't do this, we're in big trouble. Y minus 0. Okay, what about vector BP? Componentize it. Head minus tail. Head minus tail. You guys can do that? And then do exactly what it says to do. What does the 2 bars mean? The length. Okay, here's vector AP. How do you find the length of it? How do you find the length of a 2-dimensional vector? Really? Square root of this squared plus this squared. Plus, how do you find the length of this vector? The square root of that squared plus that squared. Uh-oh, we might be off the camera. Equals 10. Just to fit it on the camera, hoping that's on there. Okay, so that's your answer. Now all you gotta do is simplify it. How do you simplify this? Move one of the radicals on this side, square both sides twice, complete the square, you get your answer. So that would be one way to do it. Another way is, hey, this is something we learned last chapter. If this distance plus this distance is always 10, hey, isn't that the definition of an ellipse? The sum of the distances is constant. You guys remember that? Well, if you don't, then just do this and grind out the algebra and you get the answer. But if you remembered what we did last chapter, hey, these are the 2 foci. Therefore, the center has to be at origin. And what kind of ellipse is it if the 2 foci here? Is it just a left-right ellipse? So there's the center. And what's this constant here again? I don't know. I looked at the notes, Mr. Park. That's 2a. So if 2a is equal, why am I doing the problem for you? A is 5. And what is the distance from the center to the focus? Which is c, right? So we know c is 4. And if you know a and c, can you figure out b? Yeah. So yes, you can do the problem this way, but if you remember something, you can do it a lot faster if you do this. So I'm gonna leave it up to you. That's what happens when you purge. And then when you do number 5, do the same thing, componentize those two vectors, and then do exactly what it says to do. Add them together, and then find the length of it. That's the answer. All right, the bell's gonna ring in 1 minute. Like I said, luckily we have a short lesson today. So if I remember correctly, if the next lesson is the cross product, the other kind of multiplication, then that's a pretty intense lesson.
Thank you.
Okay, see you tomorrow.